You've seen how to obtain an upper bound on the worst-case runtime for a given algorithm. What's often harder is showing a lower bound on the worst-case runtime for a problem. Note that the kind of lower bound we're looking for here is problem-based, not algorithm-based. Finding a lower bound on a runtime to solve a problem answers the question of whether it's possible we can do better, come up with a better algorithm, a more efficient one. Let me give you a hypothetical scenario. Say you work at a company and your boss asks you to improve some algorithm to make it run faster. You spend months trying to do so, but without success. After maybe 1 year, you tell your boss you could never come up with a solution. It doesn't look good for you. But there's two sides to this coin. One side is to come up with an efficient solution. The other side is to show that it's really the best possible solution. It would be much better to, after trying for a few days without success, start to question if it's even possible to do better. After all, if you can't come up with a better solution, maybe there isn't one. You could return to your boss with such a proof and say, "I tried, but it turns out it's not possible. Here's why." It reflects much better on your algorithmic skills. So we're going to see an example of this today with sorting. You've seen a few problems now, a few solutions now to sorting using selection sort, insertion sort, heap sort, merge sort, quick sort. And so far, the best runtime that you've seen is big O of n log n. So the question is, can we do better than this? Note that sorting is just taking some input of n elements and putting them into a particular permutation, which satisfies that the first one is less than or equal to the next one, less than or equal to the next one, and so forth. So we're just taking a sequence and putting it into a specific permutation. Now, everything that you've seen so far, the sorting algorithms that we've covered so far, are all comparison-based, meaning in order to figure out what order objects go in, they make a comparison between two objects. Is this item less than or equal to this item? Makes sense when we want to put them in this specific order that we would use a comparator. So what we're going to do in this video is derive a lower bound on the running time of any algorithm that uses comparisons in order to sort elements, meaning we're going to find a lower bound on the worst case runtime of any algorithm, not just the ones that we've talked about, but any of the ones that would use a comparator. And how we're going to do that is we're going to count how many comparisons we would have to make in the worst case. So we're going to model a decision tree. So this isn't an execution tree. This is modeling at each node, we're going to make a comparison between elements. So in the first node, we check to see, is this item less than the other item? If it's true, then we're going to move to the right and we're going to make some other comparison. If it's false, then we're going to move to the left and we would make maybe a different comparison. So each run of an algorithm, doesn't matter which comparison-based sorting algorithm we're talking about, will correspond to a root to leaf path. And I'm not showing it here, although you'll see it in the next example, but each node will have stored with it all possible orderings consistent with the comparisons we've made so far. So at the root node, this will have every possible permutation of elements. And let's say at this node here, we'll have every possible permutation of elements which satisfies that xi is less than xj. Maybe xi comes much earlier than xj, or maybe it's immediately before, but all possible permutations satisfying that comparison. And at each leaf, that will contain the result of all of the comparisons that we've made so far. Each leaf would correspond to one permutation of elements that we have. So at every internal node, we make some comparison and we choose to go either to the left or the right based on the result of that comparison. So how many comparisons would we have to make? This would be a root to leaf path. How many comparisons would we have to make in the worst case? So let me show you an example of what this decision tree would be for one particular algorithm for, let's say we're using in-place insertion sort. And we have three numbers, A, B, and C. These could be anything. They could be in any order. Maybe A is smaller or B is smaller. So the first node, our root node, contains all possible permutations of how A, B, and C could go together and what order they would go together. Now remember, with insertion sort, our first step will be to kind of go from left to right, insert the element into a sorted sequence. So first we insert A. A, just by itself, is already ordered, so we don't have to do anything. Then we'll go to insert B. We're kind of work our way down this list. So when we go to insert B, we have to determine where B belongs in this sorted list. So we're going to compare it to A. So this is our first comparison, according to insertion sort. Selection sort, this may do something different. So we'll compare A to B. If A is less than B, then that means, according to our insertion sort, A is less than B, we can place B immediately after A. This is our sorted list, and then we'll move to C next. And then in that case, we'll compare C to B to determine where C belongs in this sorted list. So this is one possible branch we could take. If A is less than B, we would go here, and then we would compare B to C. If B is less than C, then great, we already have a sorted list A, B, C. But if B is not less than C, then that means we have that B is greater than or equal to C. Maybe C belongs before B, but where before B? Immediately before or before A? We need another comparison in order to determine which one of those situations we're in. So in this case, we have C is immediately before B. Here we have C comes much earlier than B. So which one would we need? So this is one example of decision tree. Again, the execution of our insertion sort algorithm follows one path here, from the root down to some leaf. Which leaf we wind up at is based on whatever our original input is, but this will give us the total order of elements. So in this case, B is less than C is less than A. So we want to figure out what the height of this decision tree would be for any algorithm, not just insertion sort, but any comparison-based algorithm. How many comparisons would we have to make in the worst case? Well, we can use the properties of a binary tree that we know. Remember, for this decision tree, we have that every internal node has exactly 2 children, and what we've seen from previous videos is that the number of leaves that we have is at most is at least 2 to the power of the height of our tree. So how many leaves do we have really here? Well, this is based on how many permutations we have. So we're given n elements, and how many possible permutations of those n elements we have is, well, we could pick whatever the first item is going to be, and there's n choices for that. Then we pick whatever the next item is going to be, and since we've already fixed the first one, we have n-1 choices for the second one. Then we pick the next one. We've already chosen 2 items, so now we have n-2 choices for the next one. And we multiply each of these together because we have to perform each one of these tasks. So the total would be n factorial. So this is how many different permutations we have, which is how many leaves we have. So this is the number of leaves in our tree. And we know from the property of binary trees that the number of leaves in our tree is less than or equal to 2 to the power of the height of our tree. Now we want to figure out is what the lower bound on the height is. So we want to solve for h here. So we're going to take log base 2 of both sides. So we have log base 2 of 2 to the h power is h, and log base 2 of n factorial. Log base 2 of n factorial. Now we can solve, kind of continuing on the right side here. So I've sort of skipped a step here, and this is replacing that n factorial is greater than or equal to up to some constant n to the nth power. So n factorial, it's known as big O of n to the nth power. Let me kind of show you what intermediate step I used here. I used that n factorial is big omega of n to the nth power, meaning it's greater than or equal to up to some constant coefficient, which we drop later, n to the nth power. And we can show this because n factorial, this is equal to n times n-1 times n-2, all the way down to 2 times 1. Now I can say that this product is greater than or equal to if I were to only take the product of some of these numbers, not all of them. Let's say I take the first half here. So I have n times n minus 1 times n minus 2 all the way down to, instead of going all the way down to 1, I'm only going to go down to n over 2. So definitely I have a larger number up here when I'm multiplying by more numbers. And I can say that this is greater than or equal to if I replace each of these n over 2 items that I'm multiplying together with the smallest value, which is n over 2. So here I have now n over 2 times n over 2. I do this n over 2 times all the way back down to n over 2. So each number that I had here, some of them are larger, I replace that number with n over 2. And this is equal to n over 2 to the power of n over 2. Now we end up getting rid of these constant coefficients when we put this in big O or big omega notation. So we just showed that n factorial is greater than or equal to up to some constant number, n to the nth power. And we know from rules of logarithms that any exponent inside here, we can move and make this a coefficient to our logarithm. So this n, we can move to as a coefficient right before log base 2 of n. So this means that the height of our tree, h, is greater than or equal to some constant number times n log base 2 of n. This means that our height is the lower bound for our height. Our height is at least some constant times n log n. So h, our height of this decision tree, is big omega n log n. So what does this mean with respect to a comparison-based sorting bound? Since the height of our decision tree is at least n log n, then every comparison-based sort would require at least n log n steps, n log n comparisons in the worst case. So we showed that the height of our decision tree, if we have n factorial leaves, which is how many permutations we have of n elements, that the longest possible root to leaf path, here's the root of our decision tree, we follow some steps to the left and the right based on how many, based on the comparisons we make. The number of comparisons that some comparison-based sorting algorithm takes is based on the length of this path. And the longest possible path that we could have is the height of our tree. And we know that that's at least n log n times some constant. So every comparison-based sort requires this many comparisons in the worst case. So we couldn't come up with a sorting algorithm yet that uses less than n log n, runs in less than n log n time in the worst case. And if we're using a comparator, it's really not possible to do that. So if we want to do better than n log n in a sorting algorithm, we'll have to do so without using a comparator. And you'll see how to do that in the next video.